Now, let's say you are given a plane surface. It could be a plank or any plane surface that is inclined at an angle theta degrees to the horizontal. This is horizontal. Okay? And then there's a block of mass. An object is placed on the surface. It's possible that this object of mass is initially stationary. It's not in motion yet. Now, I want to analyze this diagram for the forces that are acting on this system, that is, on this mass. First is the weight of this mass. The weight of a body always acts at the center of gravity of the body. Sometimes we call that center of mass. Now, just like the weight of a human, it acts along or around the navel of that individual. Now, for this body, this is center of mass, and then since weight is a vector quantity, it's good to use a line segment and an arrow head to represent the weight of a body. Recall that the weight of a body always acts vertically downwards. Hence, the direction of this line, that is the arrow. Okay, suppose the weight of the body, I use the letter W, which is also equal to mass times acceleration into gravity, or mass times gravitational field strength. Any of these can be used to define, to calculate the weight of a body. Now, this body rests on this inclined surface. The weight of the body, part of it is pressing down on the surface. We'll expect the surface to react. We call that the reaction, the normal reaction from the surface. And the normal reaction is a type of force from Newton's third law of motion, that action and reaction are always equal and opposite. And one thing about normal reaction, I use my symbol R to denote normal reaction, is that normal reaction always acts at right angles perpendicularly to the surface on which the body or the mass is placed. That's the normal reaction, which means the line of action of the normal reaction is not the same. It's not along the line of action of the weight of the body. The weight line acts along this line, normal reaction along this line at right angles to this plane surface. So that I have this angle here, this angle theta, which is the angle of inclination. The angle of the slope is the same as this angle theta in degrees. So you can see that now that we have listed two different forces, the normal reaction and the weight of the body. Now we need to resolve, it's possible to resolve the weight of the body into two perpendicular components, because there's a component of the weight of this body that acts along the plane, that acts parallel to the plane. And then we have another component of the weight that acts perpendicular to the plane, that acts in such a way as to balance the normal reaction. So if I'm to resolve the weight line, I may just draw something like this to make up this, to complete my right angle triangle. This is my angle 90. Okay, the weight line is acting along the hypotenuse. This is the opposite side. This is the adjacent side. So by SOHCAHTOA, I have the sine theta. Sine theta is equal to the opposite. Now, this opposite side is parallel to the plane surface. It's parallel to the inclined plane. So I can call this my WF, my WX, because that's the component along the plane. So my WX over the weight of the body, which is mg. So my WX is equal to, if you cross multiply, means mg, if I cross multiply, that is mg sine theta. Okay? So this component WX, that's the component of the weight of the body, of the weight of the mass, that acts along the plane, that acts parallel to the plane. I can place it like this and draw this, so that is the same thing as the vector, as the force that is acting in this direction. So this is still my mg sine theta. Now, what's the importance? What's the significance of this mg sine theta? Suppose the block is just resting on this slope, on this plane, and that the plane is smooth. There's no frictional force on this plane. Of course, when you drop this block, The moment you drop it, it starts falling down. I mean, it starts rolling down along the smooth surface. And Newton's laws of motion says that a body cannot move unless a force acts on it. So that pulling force, when this block is just dropped on this platform and the platform is smooth, the block will just on its own, you don't need to give it a push. On its own, it slides down. The sliding force, that force that produces that sliding motion of the block is the mg sine theta. Or here is Newton's laws of motion will have been invalidated if that is not there. Okay, so that's the force that causes the mass to slide down the plane, and we say it is a component of the weight that acts parallel to the plane or along the plane. Okay, so resolving and finding this other side, okay, using cosine now, let's say cos theta this time around, let's call this wy. The component of the weight that is perpendicular to the plane is wy, that is adjacent over hypotenuse, wy over mg, which is the weight. So that my wy is equal to mg cos theta. Now this is my mg. My mg cos theta is the component of the weight mg, which acts along this line. That's the component acting along this line perpendicular to the plane, and that's the component that balances the normal reaction. So that when this block is placed on this surface, notice that there's no motion along this line. The block does not accelerate along this line. Rather, the only way motion is possible, the motion of the block is possible, is along this plane. So we can see that the mg cos theta is balanced by the normal reaction R. And then if there's no frictional force, let's look at case 1. When the plane is smooth, okay, the surface of the plane is very, very smooth, such that the frictional force acting between the two surfaces is 0, or the coefficient of frictional force, whether static or dynamic, is 0. So we have again that mg sine theta is equal to the according to second law of Newton's second law of motion, ma, if the block is smooth. So, and since motion is possible along this line, it means that mg sine theta is equal to ma. M cancels m. It means the acceleration of this block down the plane is given by g sine theta. We can call this equation 1. How do they, in fact, you may be asked to answer question using this equation. For instance, they can say a block of mass, let's say 5 kg, slides down an inclined plane, a plane that is inclined at angle 30 degrees to the horizontal. This is how they can ask this question that requires the use of this equation. They'll say calculate the acceleration of the block of mass down the plane. Calculate its acceleration A down the plane. What's the acceleration of this block of mass down the plane? Suppose a block of mass 5 kg slides down a plane inclined at 30 degrees to the horizontal. Okay, so since the plane is smooth along an inclined plane, along a smooth, I would have to use the word smooth inclined plane, very smooth. That means this equation 1 applies, no frictional force acting. The acceleration of the block is g sine theta, and if g is taken as 10 meters per second squared, it means acceleration is 10 times sine 30. That is 10 times 0.5, which is 5 meters per second squared. And they may go further to ask you, suppose the block starts rolling down from rest, and probably they give the length of the plane. If the length of the inclined plane, okay, you can see the length of the plane, from here to this point, the length of the inclined plane there is given as, let's say, 10 meters. They may ask you to calculate the speed of this block just before it leaves the plane. If it starts from rest, u is 0. We've already known our acceleration to be 5. Calculate the speed of the block just before it leaves the plane. So the length of the plane is same thing as the distance x, or the displacement. Using the third equation of motion, v squared equals u squared plus 2as. So we have my v, that's what I'm looking for, equals 0 squared, which is 0, plus 2 times acceleration, which is 5 times distance. That gives me 10. So that gives me v squared equals 100, and v square root of 100 gives me 10 meters per second. So that gives the speed, that gives the velocity of the block before it leaves the plane. So with the idea of the forces acting, Newton's second law connected with kinematics can be used to solve problems in this case. We have just dealt with the case where the plane is very smooth, frictional force is absent. Now let's see a case where there's frictional force acting, that is, we are dealing with the plane surface that is rough. Frictional force acts. Frictional force acts on plane surface, so that the plane surface is rough. Is rough. So we need to do the analysis again. Okay, come back here now. Okay, let me quickly redraw it. So we have this, the plane surface inclined at an angle theta degrees to the horizontal. Okay, let's say this is the block that is lying on the plane surface, and then you see there's frictional force acting. Okay, let's take the weight of the block again, acting downward. I take the weight as mg, and then the normal reaction, of course, it acts at right angles perpendicular to the surface. Normal reaction, I call that R. Then I produce this such that I can decide to make this up to a right angle triangle. Okay, we have derived this as mg, that the component of the weight acting perpendicular to the plane. We have shown that it's mg cos theta, and this is mg sine theta. That is the component of the weight that acts along the direction of motion. Now, suppose frictional force acts. Let's say this block has been at rest, and then the mg sine theta acts this way. Okay, let's say the body or the block is just about to start sliding down. The frictional force will quickly act to oppose the motion of the block in this direction. I call the frictional force Fr. Fr comes into play when the block is just about to start sliding down. Of course, when this block is at rest, no frictional force. Frictional force only comes into play when the body slides down or tries to move over another. As long as a body is at rest, there's no frictional force at all acting. Okay, so with this now, suppose the block is just about to slide down, it's still possible to say that Fr, which is frictional force, equals mg sine theta. And by this, you'll be able to calculate the coefficient of static frictional force between the surface of the block and the plane surface. So I now have my R, normal reaction, as mg cos theta. Of course, you know that the normal reaction is balanced by mg cos theta. With these two equations, we can go ahead to determine the value of the coefficient of static friction. This is the case where the body is about to start sliding down. But when we divide these two, we have Fr, which is frictional force for normal reaction, equals mg cancels mg. The ratio sine theta over cos theta gives tan theta. And then we know that frictional force Fr, in the last video I said it is given as mu, that is the coefficient of friction, times normal reaction. Okay, so when we replace mu, which is given as the ratio frictional force for normal reaction, if I replace this with mu, I have the coefficient of static friction. Let me call that mu s equals tan theta. So these are to show that the coefficient of static friction acting between these two surfaces, the surface of the block and the plane surface, is given by tan theta. That is just when the block is about to start sliding down. Now, suppose I want to determine the coefficient of kinetic friction, okay, or kinetic frictional force. What we did here is that of static friction. Now, kinetic frictional force is that frictional force that must be overcome in order to keep a body moving with a constant speed. And when this body slides along this plane with a constant velocity, it means that the forces acting along the direction of motion are only two of them, mg sine theta and Fr. So when the body slides down with a constant speed, constant velocity, the frictional force that must be overcome to keep it moving with a constant speed is called the kinetic or dynamic frictional force. So to find the coefficient of dynamic frictional force, I have to equate mg sine theta, equate that to Fr, in order for me to find the coefficient of kinetic or dynamic frictional force. So I have this mg sine theta And then this frictional force is given as mu times dynamic frictional force times normal reaction mg. So this my mg cancels my mg. So the coefficient of dynamic frictional force is given as sine theta. I can see that the two of them are not the same. Suppose theta is 30 degrees. The angle of inclination of the slope is 30 degrees. So you can see that the static friction is given as tan 30, and then the dynamic frictional force mu d is given as sine 30. You agree with me that tan 30, if you confirm that with your calculator with your four-figure table, is about 0.57, and then sine 30 is 0.50. So you can now see that, just as I said earlier, that the static frictional force or the coefficient of static frictional force is greater than the dynamic or the coefficient of dynamic frictional force. Okay, the next video we're going to take more questions on these dynamics of motion along an inclined plane.